Hi students, in this session we are going to learn about resonance or mesomerism. Already in our previous session, in our yesterday's session, I had started the fundamental concepts of organic reaction mechanism, in that electronic displacement of covalent bond. So this is complete mind mapping what you are going to study about the topics. In our yesterday's session, inductive effect 2 types completed and electromeric effect also 2 types completed. Now students, in this session you are going to learn about resonance or mesomerism. In this, about resonance, what is the definition and what is the use of this resonance also you have to learn in this session, and mesomerism types. In this resonance only types plus R effect and minus R effect also you should learn in this session, and resonance structures and how we should draw the resonance structures of different ions, just like CO32 minus, NO3 minus and Nitro, Methane, and what are the structures and what are the rules we have to follow while writing the resonance structures, and relative contributions of resonance structures. About these 3 we are going to learn in this session. This is the mind mapping. Okay students, if it is possible you can copy in your notes this complete mind mapping. Just by seeing this you have an idea, you have a grip on these fundamental concepts of organic reaction mechanism. Right, let's get into the class now about resonance or mesomerism. Sometimes it is not possible to assign a single electronic, nothing but Lewis structure of a molecule which can satisfactorily explain all its properties. Okay, in such a case it has been found that the molecule can be represented by 2 or more electronic structures. 2 or more electronic structures. Okay, and in this, each one of which can explain most of the properties, but none one of them can explain all of the properties of the molecule. Okay, the real structure of the molecule lies somewhere in between all these electronic structures, which however can't be represented on a paper. Such a molecule is said to exhibit resonance or mesomerism. Thus the phenomenon of resonance is said to occur whenever for a molecule we can write 2 or more Lewis structures which differ in the position of the electrons but not in the relative position of the atoms. Okay, the various Lewis structures, none of which is capable of describing all the known properties of the compound, that is known as canonical or resonance structures. Canonical structures or resonance structures. Okay students, the actual structure of the molecule is not represented by any of the resonance structures but is a resonance hybrid. Here another word you are going to have, resonance hybrid. Of all these Lewis structures, the various resonance structures are separated by a double-headed arrow. Just like this is known as double-headed arrow. Okay, thus in the light of resonance theory, benzene can be represented as a resonance hybrid. Benzene structure you know very well, that is the chemical formula C6H6. Okay, and a resonance hybrid of the structures are known as 2 Kjeldahl structures. Kjeldahl structures, nothing but Lewis structures. Okay, and let's see here. This is the benzene structure you know very well. Alternatively, these carbons, in between 2 carbons there are double bonds, and with the representation of this double-headed arrow, and here again this is also a benzene structure, but you have to change the positions of this bond. Okay, this is first structure, this is second structure, and the third one is This is the third one. Instead of these double bonds, just we can represent it with a circle inside the benzene ring. Okay, any of these two Kekulé structures cannot explain all the properties of benzene. According to these structures, a molecule of benzene should have 3 carbon-carbon single bonds. Okay, here you can see 3 carbon-carbon single bonds. Okay, these carbon-carbon single bonds of just 1.54 angstroms length. 1.54 angstroms length and 3 carbon-carbon double bonds. Here you can see same 3 carbon-carbon double bonds like this, 1, 2, 3. Okay, these bonds of 1.34 angstroms length. Okay, but actually it has been found that all the 6 carbon-carbon bonds in this benzene are equal 1.39 angstroms. This implies that actual structure of benzene is neither represented by this first structure nor represented by this second structure, but is a resonance hybrid of these two structures. Okay students, in other words, any two adjacent carbons in this benzene are neither joined by a pure single bond, or nor joined by pure double bond, only of this pure single bond and pure double bond. As a result, all the carbon-carbon bond lengths are equal. That should be 1.39 angstroms, as I told you previously. Here I discussed with you. Okay, and lie in between carbon-carbon double bond length should be 1.34 angstroms, and carbon-carbon single bond length of 1.54 single bond length is 1.54 angstroms. Okay, the resonance hybrid or actual molecule of a benzene, here is the actual molecule of a benzene, is usually represented by the formula 3, Roman number 3. The circle inside the ring denotes completely delocalized. This is completely denoted. This circle delocalized 6 pi electrons. Okay, delocalized 6 pi electrons. Okay students, I hope you understand about this benzene resonance structures, these three. Similarly, carbon dioxide formula you know very well, that is CO2, can be written as a resonance hybrid. I am going to show you what are the structures, resonance structures of carbon dioxide. This is the structure of CO2. Here 1, 2, 3, 4. These are single lone pair of electrons here, and here also 2 lone pair of electrons. For suppose students, here 2 electrons, here 2 electrons, okay, and for suppose here 2 electrons can be transferred from this bond to here for O, and you should get here O single bond, and here carbon, and again here 1 electron also shifted to here. Then students, here triple bond will come, and here also oxygen, and here a positive ion can be formed, and here you can see 3 lone pair of electrons can be formed, just like this. By shifting of 1 electron, here negative ion can be formed, here only 1 single pair of electrons. Okay, and we can represent this same structure like this: O triple bond, C single bond, O, and if you represent the lone pair of electrons here positive charge, and here 2 electrons, and 1, 2, 3, 4, 5, 6, and minus. This is the negative ion. Okay students, you can see the structures of CO2. The resonance structures of CO2 should be like this. Due to the contributions of structures, this is 4th one from the benzene. Just I am continuing this number. Due to the contributions of the structures 5 and 6, here 5 and 6, the carbon oxygen bond in CO2 the carbon and oxygen bond in this CO2 has some triple bonds. Here you can see this is the triple bond, and here this is the triple bond. So these are having triple bond character. As a result, the carbon oxygen bond length is 1.15 angstroms. You have to remember these, students. 1.15 angstroms in CO2 lies in between normal carbon oxygen double bond length of 1.22 angstroms. So this is normal carbon and oxygen double bond length, and carbon oxygen triple bond length is, the normal carbon oxygen triple bond length is 1.10 angstroms. Okay, just like benzene and CO2, carboxylic acids also, these are showing that resonance character. These carboxylic acids, the formula you know, COOH. Okay students, these carboxylic acids may be regarded as a resonance hybrid. I'll show you the pictures now. This is carboxylic acid structure, and on this oxygen, here two lone pair of electrons. For suppose here is the shifting of these electrons like this, and here also two lone pair of electrons, and here must be a shifting of this electron like this. Okay, then what should happen, students? You can say clearly by seeing this shifting of electrons. Here R C single bond O, R single bond O, and here the shifting of these electrons here means here double bond should come O and hydrogen here. And what about the pair of lone pair of electrons? Here one pair, second pair, and third pair also, but here shifting of these electrons like this means here negative ion should be formed, and here because of this shifting of these electrons, positive ion should come. Okay, here too this lone pair of electrons. Okay, this should be represented like this: R single bond C, here single bond O, single bond O, H, and here the positive character of this can represent with that delta symbol, and here also delta minus. Okay, and this is known as resonance hybrid. Resonance hybrid, just without representing these lone pair of electrons, you can represent like this simply: resonance hybrid. Like molecules, these are all the molecules. I told you the example, just like CO2, and this is carboxylic acid COOH. Just like these molecules, and some ions also show the resonance character. Okay, and ions also, just for example, CO3 2 minus, okay, and NO3 minus. Okay, like this some ions also shows that resonance character. How they can show that character, let's see now. CO3 2 minus. Okay, then here carbon single bond O, here double bond O, here one single bond O. Around these oxygens, here lone pair of electrons, 1 2 3 4, 3 pairs of electrons. If you see this oxygen, here pair of electrons, here also lone pair of electrons. For suppose a shifting of these electrons towards this oxygen, and here also this from this shifting of these electrons like this, and around this oxygen 3 lone pair of electrons are located. And students, it is the structure CO3 2 minus, means here 1 minus and here also 1 minus. Okay, from this you can draw the next structure of the same CO3 2 minus by shifting of these electrons. Here single bond, here single bond, here double bond O. Now the pair of electrons, lone pair of electrons upon this 2 3 pairs of electrons. So here negative charge. And if you shift this bond towards like this, and here also pair of electrons, second pair, third pair, and minus charge, then you can shift these 2 pair of electrons towards this bond. Then the final structure should be from this structure we can draw the structure of this CO3 2 minus, and around these oxygens here one pair of electrons, 2 3 pairs of electrons, lone pairs, and here must be a negative charge. Okay, due to this shifting of this pair of electrons. Okay, and if you see this oxygen here, 1 2 pairs, lone pairs of electrons, here 3 pairs of electrons with negative charge. Okay, and this is also represented like this. Here one carbon, oxygen, here single bond, oxygen, with this symbol delta minus, and here also with delta minus. Okay students, and here you no need to represent again these lone pair of electrons. So these are the resonance structures of CO3 2 minus. Now the resonance structures of NO3. Now NO3 only, NO3 minus. Okay, resonance structures of NO3 minus. Let's see. First of all, here N, single bond O, double bond O, here single bond O. Around this oxygen, here 2 lone pair of electrons, and here 3 lone pair of electrons, and here again 3 lone pairs of electrons. If you shift these electrons just like this, and this pair of electrons towards this single bond, and here must be negative charge. Okay, from this, what is the structure you are going to draw? Here N, single bond O, and here double bond O. Why? Because the representation of this arrow mark, the shifting of this lone pair of electrons like towards this single bond. And here students, you can see 2 pairs of 2 lone pairs, and here is the positive charge, and here 1 2 6, so 3 pairs of electrons with negative charge, and here also same 6 pairs with negative charge. So if you shift this pair of electrons towards this bond and like this, now what is the final structure we are going to have? That should be nitrogen here with positive charge, oxygen, double bond O. Why? Because here shifting of this pair of electrons towards this bond, so here that single bond becomes double bond, here single bond O. On this oxygen, 1 2 3 4 5 6 electrons with negative charge, 1 2 3 4, 2 pairs of electrons here. Why? Because due to this double bond. And here same as usual, 3 pairs of electrons with single bond. Okay, this structure simply we can represent like nitrogen, here single bond O, again single bond O. Okay, here we have the positive charge and delta minus, here also delta minus. Okay, and without representing the lone pair of electrons, you can represent NO3 minus ion resonance structures like this. Okay students, now the third one, resonance structures of nitromethane. Resonance structures of nitromethane. Let's see now about this nitromethane. The structure is CH3, N, double bond O, single bond O. On this oxygen, if you see the pair of electrons, only 2 pairs of electrons. Here in this oxygen, 1 second pair and third pair with negative charge. Okay, this is always positive. Okay, and here the shifting of these electrons towards this bond, and here just like this. The structure, the small changes in this structure is CH3 minus, sorry, here is the bond, okay, and here single bond, here this is the single bond, and here double bond plus, and here oxygen. Okay, due to the shifting of these electrons, here 1 2 3 4 5 6 with negative charge, and here already double bond has formed, then only 2 pairs of electrons should be formed. the final structure, the resonance hybrid structure, how we can write CH3 single bond N. Here as usual the positive ion, here single bond oxygens O, and here you can represent with delta negative, delta minus. Okay, without representing these pair of electrons you can represent like this. And students, these are the resonance structures of some ions, CO3 minus, CO3 2 minus, and NO3 minus, and nitromethane also. Now let's see about the resonance energy. These are the final resonance hybrids, and a resonance hybrid or the actual molecule is always more stable than any one of its canonical structures. Okay, canonical structures nothing but hypothetical or imaginary structures. Okay, this stability is due to the delocalization of electrons and is measured in terms of resonance energy or delocalization energy. So basing upon this resonance hybrid we can say that resonance energy. Now students, let's see the rules for writing the resonance structures. What are the rules we have to follow while writing the resonance structures? Now first one is the various resonance structures should differ only in the position. You can say that differ only in their position of the electrons and not in the position of atom or nuclei. Okay, you can understand easily the various resonance structures should differ only in their position of electrons and not in the position of particular atom or nucleus. That is the first one. Now second one, all the resonance structures should have the same number of unpaired electrons. Unpaired electrons means the electrons which is not involving, not participating in that bond, those are called unpaired electrons. Okay, if you draw all the resonance structures like this, and this also same number of unpaired electrons, and this also like that, all the resonance structures should have the same number of unpaired electrons. That is second rule. Now the third one is, in case of atoms of the second period in the periodic table, such resonance structures which violate octet rule should not be considered. Okay, octet rule should not be considered. For example, here CH2 single bond CH single bond NH3 plus, and this is the first structure, that means structure 1, and from this double bond if the electrons are shifted like this, okay, and here CH2 single bond shifted, the bond shifting means here positive ion should be formed, CH double bond NH3. This is second structure. Okay, structure 2, this is the second structure, cannot be considered as a resonance structure since it volatiles the octet rule, because nitrogen has 10 electrons in the valency shell. In other words, nitrogen can't have more than 8 electrons because it does not have d orbitals. Okay, d orbitals. Nitrogen, you know, nitrogen 7, 1s2, 2s2, only 2p3. It doesn't have d orbitals. Okay, this is rule number 3. Now rule number 4. Rule number 4, what we have, as far as possible all the resonance structures should have nearly the same energy. Okay, the more the number of resonance structure, more stable in the resonance hybrid. Here this is the resonance hybrid. In general, the various resonance structures contribute to the resonance hybrid in proportion of their relative energies. Okay, once we have to check the mind map, what I have written here, rules for writing resonance structures completed. Now relative contributions of resonance structures, let's see. we shall discuss point wise. The first one is the structures which are distinguishable or of equal energy and hence contribute equally towards the resonance hybrid. For example, equal energy. So if I take the example of benzene like this, and here are the bonds alternatively double bonds. From this, the shifting of bonds just towards like this, from here to there and from here to there, and the formed structure is just the shifting of these bonds like this. Okay, this is the example of benzene, and the next example is CH2 CH double bond CH2. Here if you shift this double bond like this, here positive ion should be formed, and the formed structure is CH2 double bond CH single bond CH2. That positive charge will come here. Okay students, this is about the first one, relative contributions of resonance structures indistinguishable with equal energies. Okay, now number 2 is structures with greater number of covalent bonds. For suppose greater number of covalent bonds contribute more towards the resonance hybrid. Let's see the examples now. The first one, CH2 double bond CH single bond CH double bond CH2. Okay, and if suppose the shifting should be like this towards this carbon, this is structure 1, then the formed structure should be CH2 single bond CH double bond CH single bond CH2. Due to the shifting of electrons, here positive plus will come, here negative minus will come. So this is second structure. From this CH2 single bond CH double bond CH CH2, we can represent just by shifting these plus and minus like this, here minus here plus, these two are same. Okay, since the formation of bond is accompanied by release of energy, therefore structure 1 with 2 pi bonds, here with 2 pi bonds is more stable than structures 2 and 3. So this is more stable than 2 and 3. Okay, which contain 1 pi bond each. Hence structure 1 makes more contribution towards the resonance hybrid than these two structures. This is number 2, second step. Second point I have explained to you. Now number 3, structures which involve separation of positive and negative charges are of higher energy and hence contribute little towards the resonance hybrid. For example, contribution of this second structure and third structure which involves separation of positive and negative charges is much less than the structure 1 towards the resonance hybrid. Okay, this is 1,3-butadiene. Okay, similarly you can see the structure of R C double bond O H, R C O H. Here the lone pair of electrons 2, and here also 2 pairs. The shifting of bond like this, and here okay, then this is the fourth one, and from this what is the final structure you are going to have? R single bond C single bond O double bond O, here H, and coming to electrons 1 2 3 4 5 6 electrons with this negative charge, and here with positive charge only 2 lone pair of electrons. This is number 5. This is rule number 3 in the relative contributions of resonance structures. Okay, let's see the mind map once. Here, the relative contributions of resonance structures, just now we are discussing about this. Now let's see rule number 4, what we have. Lesser the separation of positive and negative charges, more stable. Okay, here lesser the separation of positive and negative charges, more stable is the resonance structure. Just for example, out of the resonance structures, here number 7 and 8. Already I have drawn here from this 1-methoxy-buta-1,3-dione. So this is methoxy group. Then here 1, 2, 3, 4 carbon atoms are presented here. So the root word is but. Then here from basing upon the shifting of electrons like this, then the formed resonance structure should be like this, and this is the 7th one, and here the final structure is here, this is the 8th one. This is more stable and here is less stable. Okay, this 7th and 8th for 1-methoxy-buta-1,3-diene, which have the same number of covalent bonds. If you count the covalent bonds here, those are having same number of covalent bonds. Now here the structure 8 is more stable than structure 7, since it involves less charge of separation. Okay students, this is about number 4, 4th rule. Now let's see about 5th rule. When atoms of different electronegativities are involved, the structure with negative charge, which is having the negative charge on the more electronegative atom, and positive charge on the less electronegative atom, is of lower energy and hence contributes more towards the resonance hybrid. This is RH, means nothing but resonance hybrid. Okay, and the alternative structures in which the charges are reversed here, for example structure 11, if you see here, already the resonance structures I have drawn here. This is structure 11, this is 10, and this is 9. From this is most important one, and by the shifting of electrons towards this oxygen, then we should get like this. Here negative ion should be formed. This is less important and this is least important. This is less important, this is least important. Okay, then charge on the more electronegative oxygen atom and this negative charge on the less electronegative carbon atoms contributes less towards the resonance hybrid of ketone. Resonance hybrid of ketone, and this is from 9th structure. Here from this structure as compared to the alternative structures of 10 with the charges reversed. Here I can represent it already. Okay, now let's see what is the rule of this number 6 rule. Number 6, let's see now. Structures which help to delocalize the positive charge make important contribution towards the resonance hybrid, regardless of the fact whether the positive charge is less, or for suppose positive charge is less or more negative, more electronegative atom. For example, see this structure. Here these are the lone pair of electrons, and from this the shifting of these electrons towards this bond, and the formed compound should be CH3 twice C double bond O. Here positive charge, here hydrogen. And what about these lone pairs of electrons? Here only one pair. Okay, and this is about rule number 6. Structures having like charges on adjacent carbon atoms are highly unstable and hence contribute little towards the resonance hybrid. For example, in this structure R, C double bond O, again C double bond O, here R. Okay, if you represent the lone pairs of electrons on this oxygen atom, 2 pairs, and here also 2 pairs. If this bond shifts towards like this and here also same, then the formed structure is R single bond C, and here C again R here, and here single bond O. And here the possibility of formation of negative charges takes place. And what about the lone pairs of electrons here? 3 pairs of electrons should be located here on the oxygen atom. So the names of these compounds, here you can see 1,2-diketone. Here ketonic groups are located, arranged. So this is most important structure, most important one. And this is negligible contribution. So you can write like this, negligible contribution. Okay students, these are the rules of the contribution, relative contributions of resonance structures in this resonance or mesomerism. Now let's see clearly about this resonance. In case of conjugated system nothing but they are having alternate sigma bond and pi bonds. The electrons can flow from one part of the system to the another due to the resonance. Okay, and the flow of electrons from one part of the conjugated system to the another, creating centers of low and high electron density due to the phenomenon of resonance, is known as resonance effect or mesomeric effect. Okay, this is two types, as I told you, plus R effect and minus R effect, or plus M or minus M. Let's see first one here. Groups which donate, here are the examples. Groups which donate electrons to the double bond or to a conjugated system are said to have plus R, and these are the examples here: SR, SH, NH2, NHR, and these are all the examples of donating the electrons. Here if you see the example, CH2 double bond CHCl, from this the transfer of electrons like this, then the formed resonance structure should be, here is the positive ion, here is the negative ion, so this is plus R effect. And if you see the negative minus R effect, groups which withdrawing electrons, so these are the groups withdrawing electrons: CO, CHO, COR, cyanide group and nitro group. Okay, from a conjugated system toward themselves due to the resonance are said to have minus R effect. If you see the examples for this, here CH2 double bond CH, here the transfer of electrons like this, and from this also transfer of electrons, here the lone pair of electrons, then here positive ion should be formed, and here are the lone pairs of electrons. Okay, and this is known as minus R effect. Okay, this is about resonance effect or mesomeric effect. In that two types also, plus R effect and minus R effect. Okay students, in this session just we have finished the topic of resonance, completely the topic of resonance or mesomerism. Okay, if you understand this class, if you like this class, you can share your views in the comment section, and please subscribe to this channel for my further updates. Thank you so much. In our next session, I'll be finishing this hyperconjugation. Thanks for watching.